Well, here we go on our unit on fluid mechanics. In this unit, we're going to be looking at fluids, which are just gases and liquids. We're going to start by looking at pressure in fluids. From there, we're going to move on to how to measure pressure. From there, we're going to look at buoyancy and the buoyant force. And then we're going to move into fluid dynamics, how fluids flow. There's a lot of kinds of hydraulic devices, such as brakes in cars and lifts that move heavy equipment that make use of the properties of fluids. And a good understanding of the properties of fluids is needed to design such devices. There are three big principles that we're going to take a look at. One's Pascal's principle, another's called Archimedes' principle, and finally Bernoulli's principle. Throughout the unit, we're going to be focusing on being able to do these items right here. So make sure you've got your notebook ready and taking notes. Pause and rewind the video as we go through it, and off we go. So to start us off, we're going to cover three basic terms and ideas. This is stuff you've probably heard previously. We're just going to go through it really quickly. Fluids are any materials that flow and offer little resistance to changing their shape. So gases and liquids are fluids. A comparison of gases and liquids, then, both are a collection of very small particles. Gases are rapidly moving around, independent of each other, all over through whatever container they're in. Liquids, those particles are a little bit closer together and exert attractive forces on one another. Gases have an indefinite shape and an indefinite volume. They can be compressed, easily changing their volume, whereas liquids have a definite volume with an indefinite shape. Liquids can flow, those molecules stay together, and conform to whatever shape of container they're in. Now, the point I really want to try to get across here is about this idea of compression. Okay, gases can be compressed or expanded. Their volume can be changed pretty easily, which is not true for liquids. Liquids are basically incompressible. This is because their particles are about as close to one another as they can get, so squeezing them together doesn't make much of a difference. In this picture over here, we see this balloon of water being pressed on, but this has more to do with the material of the container that the liquid is in. We still end up with the same volume of liquid in there, regardless of how we deform that balloon, right? But if we were to fill a rigid container with a liquid and try to compress it, we would find that we would not be able to do that. Okay, so two other terms that we want to look at are matter and density. So matter is basically stuff, right? If you take in chemistry, you may have agonized over what matter was. It's really just, it's stuff. You may have even seen or put together a whole little flow chart about matter. Look, matter's, it's stuff. Okay, enough said. Density is an important property of matter. If you were to have a whole bunch of blocks of copper, for example, each of a different size, each has a different mass, each has a different volume, but all the blocks of copper would have the same density, or more specifically what we call mass density. So mass density is mass over volume, and it's given the symbol of a rho. This is a Greek letter rho. It looks like a P, but it's not. It's a rho. Now from this, we can easily see that we can calculate mass by taking density times volume. Now the units for density are kilogram per cubic meter. Oftentimes you'll see units in grams per cubic centimeter, and we just have to convert that. Here's a conversion factor for converting grams per cubic centimeter to kilograms per cubic meter. Now, mass density is independent of an object's size. That means mass and volume are parameters that characterize a specific piece of some substance, like copper or whatever, whereas the mass density characterizes that substance itself. So all pieces of copper have the same mass density, which is different than the mass density of almost any other substance. So the mass density allows us to talk about the properties of a substance in general without having to refer to any specific piece of that substance. In your reading packet, there is a table of density values for various substances on page 3, and oftentimes if you need that density in a problem, it will be given to you, or you're calculating for it. So now let's move into talking about pressure. First of all, pressure is a scalar quantity. It does not have a direction. Mathematically, pressure is force per unit area. So we have a lot of units that we could use for pressure. We could use what's called the PSI, which is pounds per square inch. Other common units are the atmosphere or inches of mercury. In physics, we use what's called a Pascal. A Pascal is a 1 Newton of force acting on 1 square meter surface. So 1 Pascal is kind of small, so we often use kilopascals or kPa. If you look on the outside of a tire of your car, you will see that the recommended pressure on them is given in PSI, and it's also given in kPa, which is kilopascals. We're going to be talking about 2 primary types of pressure: atmospheric pressure and pressure in liquids. Now, we basically live at the bottom of a sea of air that extends up many kilometers. There's no well-defined top to our atmosphere. It just gets less and less dense with increasing height until reaching zero in the vacuum of space. So nonetheless, though, 99% of the air in the atmosphere is below about 30 kilometers. Now, atmospheric pressure is caused by the weight of the air pressing down on Earth's surface. So imagine a column of air that measures 1 inch by 1 inch, then soars all the way upward to the upper reaches of our atmosphere. Now imagine we were able to take this column of air and put it on a bathroom scale. It would, at sea level, it would weigh around 14.7 pounds. So the pressure at sea level would be 14.7 pounds per square inch. Now, it varies a little bit with altitude, but this is basically the pressure that's on us all the time. It's for every square inch of you, there is 14.7 pounds of pressure on you. In metric units, a column of air with an area of 1 square meter weighs about 1.013 times 10 to the 5 newtons at sea level then. So atmospheric pressure would be 1.013 times 10 to the 5 pascals, or 101.3 kilopascals. This 1.013 times 10 to the 5 pascals will become important to us as we do various calculations. Now, given that the pressure at sea level is 101.3 kilopascals, maybe you're wondering why the weight of the air doesn't crush your forearm when you rest it on a table. Your forearm has a surface area of about 200 square centimeters. So the force of the air pressing against it's about 2,000 newtons, which is 450 pounds. How can you even lift your arm then? Well, the reason is that a fluid exerts pressure in all directions. There's a downward force of 2,000 newtons on your arm, but the air underneath exerts an upward force of the same magnitude. So the net force is just about zero. Now, the fact that a fluid exerts pressure in all directions will be an important point as we look at pressure in liquids. Now, the study of liquids at rest is called hydrostatics. If we dive underwater, as you get deeper, the weight of the water above you exerts pressure on you. As you go deeper, the pressure increases because there's more water above you. And there's also all the atmosphere above that, right? So under the water, the pressure increases by about 1 atmosphere for every 32 feet of depth. So how does that pressure act on you? Well, we want to realize that the force due to a fluid's pressure pushes not only on the walls of the container, but on all parts of the fluid itself. So if we were to take a container of water and punch holes into the container of water, that water spurts out at right angles to that container. And it's the force due to the pressure of the water behind each of those holes that pushes that water through those holes. Now, to measure the pressure at any point in a fluid, we could use a simple pressure measuring device such as this right here, where we've got a little piston in a container with a spring. And this container is a vacuum. There's no fluid force exerted on the piston from inside. Now, because we know the spring constant and the area of that piston, we can determine the pressure by measuring the compression of the spring. So once we've built such a device, we can put it into various liquids and gases to learn about pressure. When we do that, the fluid exerts a force on that piston with that known surface area. Okay, the force compresses that spring because we know that spring constant, and because that area is known, we could use the pressure equation to figure out the pressure. And by using such a device, we'd be able to see that pressure exists at all points within a fluid, not just at the walls of the container. So that's just like tension in a string exists at all points in the string, not only at the points where it's tied to an object or held by a person. So we understood tension as the different parts of the string pulling against each other, and pressure is an analogous idea to that, except that the different parts of the fluid are pushing against each other. So we'd find that there's pressure everywhere in a fluid, not just at the bottom or at the walls. The pressure at one point in the fluid is the same whether you point that pressure measuring device up, down, or sideways, right? So whatever orientation you put that device in, if it's at the same level, same depth, it's going to have the same pressure. And then in a liquid, that pressure increases with depths below the surface. In a gas, the pressure is nearly the same at all points within the container that's containing that gas. Now this leads us to some important implications that we're going to take a closer look at in our next video as we study hydrostatic pressure. See you then.